What is electroplating? Electroplating is the process of plating one metal on another by hydrolysis, mostly used to improve the corrosion resistance of metals or for decorative purposes. Electroplating is mainly used to change the surface properties of objects, like protecting against corrosion, reducing friction, and making them more resistant to wear. Moreover, this process can also be used to make objects thinner or create new ones through electroforming. The technology used is electrolysis, which involves the breakdown of ionic compounds in molten or aqueous solutions through the passage of electricity. This method stimulates non-spontaneous reactions using electrical current and have been instrumental in discovering and producing many elements in industry today. During electrolysis, an electric current passes through an electrolyte solution to facilitate the flow of ions and enable non-spontaneous reactions. In the equipment, its main components include electrodes, cathode and anode, and electrolyte. Electrolyte is a solution containing free ion from molten or aqueous ionic substance. The ions are free to move to carry charge. The cathode is the negative electrode. The anode is the positive electrode. Electrons move in electrodes and wire in alphabetical order and move from anode to cathode. Electroplating is widely used in automobile, aircraft, electronics, jewelry, toys, and other industries. For classic cars, electroplating is an effective automobile treatment method that protects and preserves the quality of the metal beneath it. Electroplating changed the properties of the underlying metal using an electric current. This helps prevent wear and rust and prevents the wear and tear of rusty and tarnished classic cars. Electroplating can also change the visual appeal of a classic car and restore its original shine. Electroplating in jewelry can be used for many different purposes. For example, electroplating to obtain different desired colors. By compositing gold with other metals, a wide variety of colors can be obtained. Electroplating to hide surface defects or improved performance. In addition, electroplating gold has other uses. Electroplating base metals or silver-based atoms with gold to obtain the gold look of fashion jewelry and gold-plated silver. In this course, many damages might happen to workers, include lungs cancer, nasal, sinus cancer, nasal symptom unclarations, perforations, irritations, ulcer, and sensitization from skin contact. This disease was caused by exposure to hexavalent chromium. In the workplace, factors that lead to increased exposure to hexavalent chromium include atomization occurs during gold plating when hydrogen bubbles explode at the surface, causing hexavalent chromium in the electrolyte solution to form airborne water droplets. Conditions that increase atomizations include higher current, longer plating time, higher bath surface tension, higher bath temperature, and increased stringing. Second, drag out. When workers insert or remove shelves or bellows from gold-plated slots, atomization and overflow may occur. Third, adding hexavalent chromium. Adding chromic acid and chromium powder solution to the gold plating tank may cause overflow or produce dust or atomization. Fourth, work method. Using compressed air to dry parts. Not cleaning spill in a timely manner, and keep containers open can increase the amount of hexavalent chromium in the workplace. There are two conditions that can cause workers to be exposed to hexavalent chromium: inhaling mist, dust, or fumes containing hexavalent chromium, or skin contact with hexavalent chromium solutions. Based on this information, scientists give many ways to reduce and decrease the damage. First, they designed a personal air monitoring system, which related with the main concept system. This system can determine the amount of hexavalent chromium a worker might be exposed to, and the monitoring results are compared to applicable exposure limits to evaluate compliance. The results will be made available to the affected employees within 15 working days. This will help the workers know if she or he affected by hexavalent chromium or not, and if there is a problem, check and deal with it in time. The factory also has methods to decrease the damage. First way is product substitution. Factories can use fewer toxic alternatives than hexavalent chromium, and it will make the damage depleted. Second way is to reduce atomization. Factories can add chemical surfactants or wetting agents to the electroplating bath to reduce surface tension and reduce atomization to reduce chemical damage to workers. Use a nozzle to mix the chemical bath to reduce agitation and ensure a uniform bath also help protect the health of workers. The use of ventilation equipment to remove atomized matter from the air. Local exhaust ventilation is the most effective way to reduce the concentration of hexavalent chromium in electroplating operation. In addition to these methods, workers themselves can also prevent or reduce their own risk of injury. Remove parts slowly and carefully, rising parts with low pressure. Do not use compressed air for drying. Clean up spill quickly and carefully. Keep chemical tanks and containers covered when not in use. Add chromic acid to the plating bath as a solution. Avoid dry chromic acid additions. Clean surrounding work surface at the end of each shift. All this will help them to be healthy and safe, and wear personal protective equipment, PPE, is also a good method. There's another way to reduce damage. Change the method. There is one method used to replace electroplating. It's high-velocity hydrogen fuel. The environmental issues associated with hard chromium plating primarily stem from the use of hexavalent chromium solutions, which generate significant amounts of harmful waste. While chromium metal and trivalent chromium are relatively safe, hexavalent chromium solutions are recognized as human carcinogens and can cause diaphragm distortion, skin irritation, and lung irritation. The current electrolyte hard chromium plating process poses numerous hazards to environment. First, direct contact events include gas emission from bubble rupture and skin contact with plating solution. Second, toxic wastes include electroplating waste, bath dry out, waste acids and bases used in cleaning and stripping operations, anodizing lead sulfate sludge, flushing wastewater, and contaminated mask materials. Electroplating also has a significant impact on the economic. The electroplating process must remove harmful elements from waste solution and contaminated water, precipitate and evaporate them, and discharge the treated water into the sewage system while sending the solid to a toxic waste treatment plant. However, the increasing cost of transporting and disposing of toxic waste exposes companies to potentially catastrophic liability lawsuits in the future. Additionally, failed waste disposal often results in fines for unauthorized sewage discharge. These problems can be effectively addressed using fungible methods. There have many benefits of HVOF over EHC. First, HVOF has significantly higher wear resistance compared to EHC. In sliding wear tests, HVOF showed 200 times less material volumetric load than EHC. It also demonstrated nearly 7 times less volumetric loss in abrasive wear test. Second, after a 3-year corrosion assignment, it was found that HVOF thermal spray castings outperformed EHC castings in terms of corrosion resistance. Third, steel specimens coated with HVOF exhibited reduced surface damage and cracking compared to those coated with EHC during gravity impediment and ball impact tests. Also, while specimens coated with EHC experienced a significant loss in fatigue strength, those coated with HVOF showed improved performance, and a detailed cost and benefit analysis used the environmental cost accounting methodology revealed that HVOF offers substantial annual cost savings and high net present values over a 15-year period.